Okay, so hello and welcome back. So in this video we want to talk about composition of functions. So basically we can the concept of composition of functions, we can understand it using a simple example. So suppose that, for example, you have some set A which basically represents all of the students, who appeared in an examination, for example. Let's call it a board examination, because I'm going to need this term later. In a board examination. And a board means basically a board of education, what they call. In different countries it does mean different things, but or in some countries it's not used. Let's suppose that, for example, there is some board of education that basically that has some sort of, for example, entrance examination or something like that, and then this examination is done by them or under their supervision or something like that, and all the students who appeared in a board examination, set A basically represents those students. Now, each student appearing in the examination is assigned a roll number by the board. So basically each student is assigned a roll number by the board, okay? And moreover, the roll number must be written in your or on your answer sheet. On the answer sheet at the time of the examination. At the time of the examination. Okay. Now, in order to have confidentiality, basically for the sake of confidentiality, the board arranges to deface the roll numbers to deface the roll numbers and assign a fake code number to each roll number. A fake code number to each roll number. So what that means is that for the sake of confidentiality means that, for example, suppose that there are these people that correct these question papers and these answers in the examination, and suppose that some student happens to know the person who corrects the papers, and suppose that by chance, for example, his question or his answer sheet is corrected by that person, and then, for example, they could bribe him or pay him some money or do something so that that person corrects the answer sheet in such a way that the student passes the exam, even if he's not supposed to pass the exam based on the way that he has answered the questions. So if that's the case, what they do is that basically to make sure that nobody can, meaning that in order to make sure that the people who correct those papers, that they don't know to whom this paper belongs actually, so they deface those basically those roll numbers and swap them with some code number, and that code number is assigned to that roll number, meaning that the board itself knows that, for example, this code belongs to this roll number, and then when they see the code, they assign, and they know the name of the student that way. So now that's basically the situation. Now let B as a subset of n, let B as a subset of n be the set of all roll numbers. Let that be the set of all roll numbers, and let's C as a subset of n be the set of all code numbers. The set of all code numbers. Now this gives rise to two functions. So here basically you will get two functions, f as a function from a to b, and g as a function from b to c. And g as a function from b to c. Which means that, and the two functions are given by f of a is equal to the roll number assigned to the student A, the roll number assigned to student A, and f of b defined as, g of b defined as the code number assigned to the roll number B. The code number assigned to the roll number B. Okay? So that means that basically the function, basically B is a set, which is the set of all the roll numbers that the board has, and C, which is also a set of the set of natural numbers, the subset of a set of natural numbers, is the set of all basically code numbers that the board has. So what that means is that then we have two functions here. Function f from a to b defined by the roll number assigned to student A. That means that f of a is basically the domain of this function is A, which is basically the name of all of those students, and basically the range of that, or the codomain of that function, is basically the set of all roll numbers. So you have the name of all the students. So you have a set A over here, which is students students' names, and then you have this set B over here, which is basically the set of all roll numbers. All roll numbers. And you have a set C over here, which is basically all code numbers. Right? Now there is a function f from a to b. There is a function from a to b, and the function f is basically defined as f of a. Suppose that all of these elements are these elements. Let's denote them by a. Let's denote all of these elements by b. And then f of a is equal to basically f of a, which is basically some element here. So you can take it as b. So then you can say that f of a or b is the roll number assigned to the student a, right? And then we have another function here, g of b, which is the code number assigned to g of b would be the code number assigned to the roll number b, meaning that the roll number b is taken from here through function g, and basically this is g of b. This is g of b, and g of b, that the rule for function g, the function g is the code number assigned to the roll number b, right? So that means that you have the student names over here. Through function f, those student names will be assigned to some roll numbers, and through function g, the same roll numbers will be assigned to some code numbers. That's basically how this works. So now in this process, each student is assigned to a roll number through the function f, and each roll number is assigned to a code number through the function g. Thus, by the combination of these two functions, each student is eventually attached to a code number, meaning that take any a over here, through function f you get to the corresponding roll number, and through the function g you get to the corresponding code number. That means that each student of the set A will eventually be assigned a code number through the combination of these two functions, both of them put together. Now, this gives us basically a definition. This gives us a definition which we can call definition number 8. Definition number 8, which is basically let f be a function from a to b. Let f be a function from a to b, and g be a function from b to c. Be a function from b to c. And let g be a function from b to c. Let these be two functions. Then the composition of f and g, then the composition of f and g, denoted by GOF, is defined as the function GOF is defined as the function GOF from A to C, given by given by GOF of x is equal to G of f of x, which is equal to, for G of f of x, for every x belonging to A. And so you can imagine that you would have some set A over here. You would have some set A over here. You have x over here, and you would have some set B over here, right? And you would have some set C over here, and then x is mapped to f of x in B, and x is mapped to f of x in B, and then f of x is mapped to G of f of x in C. Let me write this properly. G of f of x in C. So this is basically C. So what that means is that x is mapped to, through the function f, basically x is mapped to f of x through the function f, and then through the function g, f of x is mapped to G of f of x in C, this way. This is the function g. And so you can say that the composition of these two functions f and g would be a function g of f of x would be G of f of x, which is GOF. So that is G of f of x. Okay, right. So this is not f of g of x. This is actually, you need to pay attention to the basically, first of all, I have the function f over here, then I have the function g over here, but the function that takes you from here to here is G of GOF, or G of f of x, because you have to apply the function g to f in order to get from here to here, right? Now let's do a couple of examples to understand this. So example number 15 is let f be a set, or let f be a function from the set 2, 3, 4, 5 to another set which is 3, 4, 5, 9, 9. 3, 4, 5, and 9. And g be a function, from the set 3, 4, 5, and 9 to the set 7, 11, and 15. Be functions defined as, so let these be functions defined as f of 2 is equal to 3, f of 2 is equal to 3, and f of 3 is equal to 4, f of 3 is equal to 4, and f of 4 is equal to f of 5 is equal to 5, f of 4 is equal to f of 5 is equal to 5, and g of 3 is equal to g of 4, g of 3 is equal to g of 4 is equal to 7, and g of 5 is equal to g of 9 is equal to 11. You want to find GOF, right? So we have this function over here, the function f. This is the domain, this is the codomain 2, 3, 4, 5, 3, 4, 5, 9. And g is another function 3, 4, 5, 9, and 7, 11, and 15, domain and codomain. And the functions are defined as follows: f of 2 is equal to 3, and so on and so forth. Now you want to find GOF. So how do you do that? So basically you can say that basically you know that g of 2 is equal to 3. That means that f of 2 is equal to 3, f of 3 is equal to 4, and f of 4 is equal to so on and so forth. So what that means is that the f of 2 is equal to 3, f of 3 is equal to 4, f of 4 and f of 5 are equal to 5, right? Which means that 9 is not the image of any of the members of the domain of f, right? 9 is not an image of any of the members of the domain here. Now g of 3 is equal to g of 4. So now g of 3 is basically, when you talk about g, you have these members 3, 4, 5, 9, the same members over here, and g of 3 and g of 4 are equal and equal to 7, and g of 5 and g of 9 are both equal to 11. That means that 15 is not the image of any of the elements in the domain of the function. Which means that you can say that g of f of 2 is equal to g of f of 3. Which means that g of f of 2 is equal to g of f of 3 is equal to, well, you need to write them down, otherwise you would not be able to actually do it, right? So what you want to do basically in such a situation, then basically you know that f of 2 is equal to 3 and f of 3 is equal to 4. And f of 4 and 5 are 5, right? Which means that if I were to, which means that basically, of course, all of the elements of the domain of the function must be the pre-image of some element in the codomain of the function. But it's possible that some element in the codomain of the function is not the image of some element in the domain of the function, and that still would be a function. But it's not possible that you leave any of these elements out. All of these elements, each and every one of them, must be the pre-image of some element in the codomain of the function. It has to be that way, otherwise the relation would not be a function, right? So as you can see, basically 2 is being mapped to 3. 2 is being mapped to 3 here. And 3 is being mapped to 4 here. 3 is being mapped to 4 here. And 4 and 5 are both being mapped to 5. So 4 is being mapped to 5, and also 5 is being mapped to the same element 5, right? So this element is covered, this element is covered, these two elements are covered. This element is not the image of any of the elements in the domain of the function, which is not a problem. Which means that the function is not surjective, and of course the function is not 1, 1, because as you can see, the image of 4 and the image of 5 are the same element here. So it's not 1, 1, it's not surjective, it's not, and therefore it's not bijective, of course. So what that means is that, so that is basically what's happening in F. Now in G, what's happening is that G of 3 is equal to G of 4 is equal to 7. So 3 and 4 are both being mapped to the same element 7. So that means that these two elements of the domain are simply covered. And what that also means is that the function G is not a 1, 1 function, it's a many 1 function, right? And also G of 5 and G of 9 are both equal to 11. So that is equal to 11, and that is also equal to the same thing over here, right? And again, you can see that 15 is not the image of any of the elements of the set of the domain of the function, meaning that, well, the function is not surjective, and the function is not injective either, because the images of 3 and 4 are the same, and the images of 5 and 9 are again the same. So none of these functions is injective, none of them is basically surjective, right? Now, in order to figure out GOF, you need to get from basically 3, 4, 5, 9 is the codomain of the function f. It's also the domain of the function g, meaning that the codomain of f is the same as the domain of g. So we can, and for the same reason, we can compose these two functions and put them together. Otherwise, we could not actually. Which means that now there is a problem here, and that is, you see that, for example, f of 2 is equal to 3, and then g of 3 is equal to 7, which means that f of g of 3 is equal to 7. Or basically GOF of you can say that GOF of 3 is equal to 7. So then you can say that, for example, or you can say that you can see that f of basically GOF of 2, for example, here GOF of 2 is the same thing as G of f of 2, right? Is the same thing as G of f of 2, which is equal to, now f of 2 is basically, f of 2 is equal to 3, so that means that G of 3, and I know that G of 3 is equal to 7, so that is equal to 7, right? And GOF of 3, as we wrote over here, GOF of 3 as we wrote over here is equal to G of f of 3. g of f of 3, which is equal to, basically f of 3 is equal to 4, so that means that g of 4, and I know that g of 4 is equal to 7. G of 4 is equal to 7, so that is equal to 7 as we found here. Now the next thing that we have is 4 and 5. So you want to calculate GOF of 4 and GOF of 5. So GOF of 4 is the same thing as G of f of 4. G of f of 4. And you know that f of 4 is actually equal to 5, so that is G of 5, which is equal to G of 5 is equal to 11, so that is equal to 11. Now G of f of 5, GOF of 5 is the same thing as G of f of 5, which is equal to, now f of 5 is equal to 5. F of 5 is equal to 5, so that's G of 5, and G of 5 is equal to 11, so that's equal to 11. Okay? That is equal to 11. So as you can see, what's important here to understand is that there are 2 points in this example. First of all, when you want to basically, when you have some f of x and when you have some g of x, then you can so g of 9 and g of 4 and g of 3. So as you can see, for example, g of 9 does exist here. G of 9 does exist here, but it's not used in any of these compositions, because 9 is not the image of any of the elements in the domain of F, right? So that's one point to note. And so meaning that if 9 as an element of the codomain of F is not an image of some element in the domain of the function, then even if 9 has been mapped from here to some element in the codomain of G, you still don't use it in any of these functions. As you can see over here, I end up with, for example, G of 5. Over here I end up with G of 5. Over here I end up with G of 3, G of 4, 3, 4, 5. But G of 9 is simply not there. Okay? So that's something that you need to understand. And also, moreover, when we say that GOF, that is G of f of x, right? So GOF of x would be G of G of f of x, and whatever the value of f of x is, you're applying the function g to that value, meaning that basically f of x should exist in the first place as that value, and then you can apply g to it. Otherwise, if it doesn't exist, you cannot apply g to that value, which means that well, I don't want to confuse you. Let's see a couple more examples, and then we will know more about these. Okay. Okay, so the next question that we have is, example number 16. Example number 16, it says that find GOF and FOG. You want to find GOF and FOG if f is a function from R to R and g is a function from R to R, given by f of x is equal to cos x, and g of x is equal to 3 times x squared. And also you want to show that GOF is not equal to FOG. Okay, so that's the question. Okay, so basically to calculate GOF of x, but of course you know that GOF of x is g of f of x, meaning that you have the function f of x, whatever that function outputs, you give that output as an input to the function g, and then meaning that you give that output, you give it as an argument to the function g, and then function g gives you some output relative to that input. So that means that g of f of x is equal to simply basically 3 times, so you have to put the function f inside the function g, meaning that g of f of x becomes 3 times x squared, and then g of x is the same thing as 3 times x squared, right? Now here your x becomes f of x, and f of x is equal to cos of x, which means that wherever you see x, you replace it with f of x. So that becomes 3 times cos of x whole squared, which is equal to 3 cos squared x. So and then the function f of g of x, or FOG of x, is equal to f of g of x, right? Is equal to f of g of x, and f of g of x, the function f of x is equal to cos x. Now in that function, wherever you see x, you replace it with g of x, which is 3x squared. So it becomes cos of basically 3x squared. And you can see that g of f of x is equal to 3 cos squared x. F of g of x is cos 3x squared. And of course you can write it this way, meaning that the whole angle is basically 3x squared, whatever x might be. Then you raise that angle to the second power and then multiply it by 3, and that becomes the argument of the cos function. So then you can see that f of g of x, is not equal to g of f of x, as you can see here, 3x squared and cos of 3x squared, 3 cos squared x and cos of 3x squared. And so that's basically example number 16. Now example number 17 is basically you want to show that if f is a function from R to from R minus 7/5 to R minus 3/5, So the domain of your function is r minus 7/5, and the codomain of your function is r minus 3/5, which is defined by f of x is equal to 3x plus 4 divided by 5x minus 7. And you have another function g, which is a function g from r minus 3/5 to r minus 7/5, which is defined by g of x is equal to 7x plus 4 over 5x minus 3. Now, then FOG has been defined as I of A, and GOF has been defined as I of B, where A is equal to r minus 3/5, and B is equal to r minus 7/5. Right? I of A of x is equal to x. I of A of x is equal to x for all x belonging to the set A, and also I of B of x is equal to x for all x belonging to B. Right? Are called identity functions. So these two functions A and B are called identity functions on sets A and B respectively. Are called identity functions on sets A and B respectively. So basically the question is that you want to show that if f is equal to, if f is a function from r minus 7/5 to r minus 3/5, which is defined by f of x is equal to 3x plus 4 over 5x minus 7, and if g is basically a function from r minus 3/5 to r minus 7/5 defined by g of x is equal to 7x plus 4 over 5x minus 3, then FOG is equal to FOG is equal to I of A, and GOF is equal to I of B, where A and B where A is equal to r minus 3/5 and B is equal to r minus 7/5. So you want to show that if that is the case, then this is the case, right? So then where A is equal to this and B is equal to this, I of A of x is equal to x for all x belonging to A, and I of B of x is equal to x for all x belonging to B are called identity functions on sets A and B respectively. So the solution here is that So let's go through the solution. Actually, I didn't really understand the problem completely. So let's take a look at the solution and see what they actually mean by the problem. Sometimes you can do that. Let's see if that's possible here. So the solution is basically we have g of f of x. So g of f of x is basically g of x is basically this function. This is the domain of your function. This is the codomain of your function. F of x is basically this function, the domain of your function, and the codomain of your function. That means that g of f of x becomes basically, I have to write g of x, which is this function 7x plus 4. Let me make a screenshot here so that I know what I'm doing. Okay, so if I calculate g of f of x here, so basically g of x is equal to 7x plus 4. 7x plus 4 over 5x minus 3. And f of x is equal to this thing over here, which is basically f of x is equal to basically 3x plus 4 over 5x minus 7. Right? Now g of f of x is going to be equal to basically wherever you see in g of x, wherever you see x, you have to put f of x in there. Meaning that you have 7 times this whole fraction, 7 times 3x plus 4, 3x plus 4 divided by 5x minus 7. So that's 7 times x plus 4, and then in the denominator you have 5 times the same fraction, which is basically 3x plus 4 over 5x minus 7. 5 times that minus 3. So 7 times this plus 4 over 5 times this minus 3, which is equal to basically so let's calculate, that would be equal to basically 7 times 3x plus 4 over 5x minus 7, and or I can what I can do is that I can take the LCM here as 5x minus 7 and write this as 7 times 3x plus 4 plus 4 times 5x minus 7, and then in the denominator I can take the LCM as 5x minus 7, and over here I can write 5 times 3x plus 4 minus 3 times 5x minus 7. So then you can simplify these two, cancel these two out, and then you will have 21x plus 28 plus 20x minus 28, 15x plus 20 minus 15x plus 21, and then these two will be cancelled out, you have 20x plus 20x is equal to x, and 20 plus 21 is equal to Actually, that is 41x, and that is 41. 20 plus 21 is equal to 41. That's equal to, so that is equal to x. That means that g of f of x, g o f of x is equal to x. And you can see that g of x and f of x were 3x plus 7, 5x minus 7, and so on and so forth. 7x plus 4 and 5x minus 3. We need to later find some relationship between these and see why they are called the identity functions on set A and B. Let's see why that is the case. And that is basically why we are saying here that I of A of x is equal to x and I of B of x is equal to x. So now if you calculate f of g of x, let me make a screenshot here. This is screenshot, it's way too large, I cannot make sense of it. Okay, so now we said that basically f of x is equal to 3x plus 4, 5x minus 7. F of x is equal to 3x plus 4, 5x minus 7, and g of x was equal to 7x plus 4, 7x plus 4 over 5x minus 3, over 5x minus 3. And you want to calculate, over here we calculated g of f of x. Now we want to calculate f of g of x. F o g of x, which is equal to f of g of x. Okay? So in order to do that, what you need to do is basically in f of x, wherever you see some x, you have to put g of x in there. Meaning that you can write this as in f of x, for example, that's 3 times 7x plus 4 over 5x minus 3, and then you multiply this by a 3 times x plus 4, and then 5x minus 7, so 5 times g of x, which is equal to 7x plus 4 over 5x minus 3 and minus 7. And that gives you basically, I can take some LCM 5x minus 3 here, 5x minus 3, and then that becomes 3 times 7x plus 4, 7x plus 4, plus 4 times 5x minus 3, and over here you have 5 times 7x plus 4 minus 7 times 5x minus 3, and then these two will be cancelled out, and so you will have 21x plus 12 plus 20x minus 12 over 35x plus 20 minus 35x plus 21, and these two will be cancelled out, that is equal to 20x plus 21x is equal to 41x, and 20 plus 21 is equal to 41, that's equal to x. That means that basically f of g of x, f o g of x is equal to x. Okay, so now in order to understand this example is something important that needs to be understood. There's a whole lot of there's a whole lot of basic notation here that we need to understand, and so on and so forth. So so basically we said that as we see here, f is a function from some set to another set, and g is another function from this set, from the codomain of f to the domain of f. And so there is a rule for f of x, there is a rule for g of x. We want to show that if that is the case, then f or g of x is equal to I of a. We will talk about this, what I of a means. And g of f of x is equal to I of b, where a and b are these two sets. And I of a of x is equal to x for all x belonging to a, and I of b of x is equal to x for all x belonging to a, and these are called identity functions on sets a and b respectively. Now, the situation that we have here is basically something like this. I did try to basically understand this completely, but sometimes you have to talk about something you have to talk about something in order to find the relationship between all the possible relationships that you can find in that situation. So basically what we have here is that you have some f, which is some function f that is from r minus let me write it this way, because that way things will get a little bit messed up. So we have two sets over here. Let's say that we have a set A here, which is basically r minus 3/5, and we have another set here which is basically r minus 7/5, right? So we have these two sets here. Now we have basically a function f which is from we have a function f which is from r minus 7/5, which is from b, to r minus 3/5, which is a. So the function f is from b to a, and then this way we can understand this much better. And this function f is defined by f of x is equal to 3x plus 4 divided by 5x minus 7, right? This is function f. I have another function here which is function g, which is from basically r minus 3/5, which is a, to r minus 7/5, which is basically b, from a to b. And it is defined by g of x is equal to basically 7x plus 4, 5x minus 3. Now, that is the situation that we have. Now there are a couple of notation. There is some note, and there is the first thing that we can notice here is that basically the domain of f is b, the codomain of f is a, and then g, when it comes to g, the domain of g is basically the codomain of f, and the codomain of g is the domain of f, right? So that's what we see in these two functions. And moreover, what you can see is that if you take f of x is equal to 3x plus 4 over 5x minus 7, and and if you calculate the inverse of this function, right? The inverse of this function is going to be equal to, if I set f of x is equal to y, I will get y is equal to 3x plus 4 over 5x minus 7, and then that gives me basically, if I cross multiply, I get 5xy minus 7y is equal to 3x plus 4, and if I put all of the x's together, I will get 5xy minus 3x is equal to 7y plus 4. And if I take an x out here, I get 5y minus 3 is equal to basically 7y plus 4, which if I calculate x here, it gives me basically x is equal to 7y plus 4 over 5y minus 3. Now if I write this in terms of, now this is x in terms of y, I can change my variables if I want to, as long as I know what I'm doing. So instead of x I write y, instead of y I write x. So I write y is equal to basically 7y plus 4 over 5y over 7x plus 4 over 5x minus 3. And now to make it in the, basically to make everything as we write our functions, I will write this as, instead of y I write f of x is equal to, and instead of, well, x you don't have to change that, f of x plus 7x plus 4 5x minus 3. And you can see that this, so this function over here, this is the inverse of a. This is the inverse of a. So that means that the function, the inverse of f, right? So we started with f over here and we got the inverse of f. So the inverse of f, as you can see, 7x, f of x is equal to, now here it's called g of x, but it doesn't really make any difference. Now over here you can see that g of x is equal to 7x plus 4 over 5x minus 3. Which means that basically g of x is actually the inverse of f of x. Okay, so that's one thing that you can notice here. Now the second thing that, now we have a couple of things that we need to understand here, and that is basically, provided that we know this is a, this is b, f goes from b to a, g goes from a to b, and so on and so forth, and f the inverse of g and g is the inverse of f, then what we have is that then FOG, we say that if that is the case, then FOG is equal to I of A and GOF is equal to I of B. Is equal to I of B, where I of A of X, I of A of X is equal to X for all X belonging to A, and I of B of X, and I of B of X is equal to X for all X belonging to B, for all X belonging to B, and these are called identity functions on set A and B respectively. These are called identity functions on sets A and B respectively. Right? So what that means is that now you can see that f of g of x is basically the function f of x, and instead of, you know that f of g of x is the function f of x, but that the argument of the function becomes the function g of, or the output of g of x. If you use the output of g of x as the argument of the function f of x, that is the meaning of FOG of x. Now here what they're saying is that f of g of x is equal to I of a, and I of a of x is equal to x. That gives you x for every x belonging to a, right? So I of a of x is equal to x. That means that if you have I of a of, that means that this function f o g, if I call it I of a, if the argument is x, then the output becomes an x for every x belonging to the set A. And the reason is that basically the function f of g of x, you can see that g of x is basically this function over here, and basically so f goes from b to a, right? So f goes from b to a. That means that you have some set A over here, and you have some set B over here, and f is basically a relation or a function from A to B. So that is f. Now g is from A to B. That means that g basically goes from, well, or f, or I'm sorry, I made a mistake here. So let's say that you have this function a over here and you have this function b over here. So we said that f goes from b to a. F goes from b to a. And g goes from a to b, right? G goes from a to b. So what that means is that, so now if I have some x over here, then f gives me f of x over here, right? And then I can basically, and then if I have some x over here, g gives me g of x over here. Now, if what that means is that if I take g of x and use it as an argument for f of x, if I use some g of x and use it as an argument for f of x, that gives me f of g of x. And f of g of x, which is basically this function over here. Now, what we are saying here is that I of a of x is equal to x for all x belonging to a, and I of b of x is equal to x for all x belonging to b. And these two are called identity functions, are set A and set B respectively. So I think what we can conclude here without making wrong conclusions is that well, I didn't, to be completely frank with you, I didn't understand the situation completely, except that I understood that basically f is g is basically the inverse of f of x. And so of course it makes sense that f of g of x is going to be equal to g of f of x is going to be equal to x, because whatever function, if you give, if you have some x basically in, let me show you this way. If I have this set A over here, and if I have some set B over here, and if B goes from B to A, if F goes from B to A, then let's suppose that we have some X over here, then X goes through F and that becomes F of X. Now G goes from A to B, right? G goes from A to B, and it is the inverse of F. So that means that if I calculate G of F of X, g of f of x here, that is going to be equal to x. And you can do the same thing the other way around, meaning that suppose that you have some x over here. Give it to g, it gives you g of x. Now since the two functions are inverse functions, then if I calculate f of g of x, here, of course that's going to give me x, because that's what you started with. That means that FOG or GOF is equal to GOF of x is equal to FOG of x is equal to x. Now there is these two business of this business of identity functions on sets A and B that remains to be understood, and hopefully we will understand them through some other examples, but you do need to make sure that you pay attention to these examples and analyze them as closely and as much as you can, because these are important concepts. Okay, so so this was example number 17. We will most probably come back to this example again and study it again. So in the next video, we will continue with example number 18. I'll see you in the next video. Thank you.